today I want to talk about Oblivious RAM and how it evolved from, pure on-paper theory to large-scale real-world deployments. Okay, so I will begin with Signal's success story of deploying Oblivious RAM, or ORAM for short. And then we'll walk through how to construct Oblivious RAM together. And then at the end, I will talk about, the potential applications of ORAM in blockchain context. Okay, so let's first look at Signal's story. Signal, so actually there's some echo.
We can turn off my.
Maybe what I will do is I will turn off the sound on my side. So, okay. Okay, so let's first look at Signal's story. Signal is a private messenger app. I guess many of you may be familiar with it. And they want to offer private contact discovery. And you must be familiar with contact discovery too, right? So when you sign on to Signal, they will ask you to upload your contact address book. And so they can discover, which of your friends are also using Signal, and you can then connect with your friends. But the problem is the user, in this case, it's Vitalik. He may be privacy aware, he doesn't want to disclose his address book. Okay, so how can we enable contact discovery, but without having to leak the address book to the server? So here's a strawman idea. Suppose, let's say you have a secure CPU like Intel SGX on the server side. So one thing you can do is you can encrypt your database. Let's say you have this user database that contains all users' information. The database, let's say it's encrypted in memory and on disk. And inside the secure processor, the secure processor creates a hardware enclave. So inside the enclave, there is a secret decryption key, which can decrypt the data and do the computation to find your friends. But the point is, as soon as any data leaves the enclave, it will become encrypted again. And the communication between the user and the enclave, of course, is also encrypted. Okay, so this way, essentially, you're essentially using trusted hardware to perform computation on encrypted data. And the hope is that nothing gets revealed if the data is encrypted. But it turns out that for this particular application, it's not the case. It's actually well known that access patterns to even encrypted data can leak very sensitive information. So the problem in this example is that even though the data is encrypted, let's say the operating system can observe access patterns when the enclave fetches memory pages from outside the enclave. So you can see which user records are being accessed. And even though the user records are encrypted, just observing which records are accessed will leak everything. It will leak, who are your friends. It will leak the social network graph. Okay, so this problem is called access pattern leakage. And it's not only a particular problem that Signal encountered, it is actually a very general problem that it appears everywhere, essentially. So for instance, we can imagine a very simple program like binary search. You don't have to look at the code, but this is just binary search. You look at the middle elements, and depending on the result of the comparison, you either recurse on the left half or the right half. And by observing the sequence of access patterns, you can learn, what is the rank of the element you are searching for. So this also basically completely leaks the query, right? Even if the data is encrypted, as long as you can observe the access patterns. Okay, and more generally, from a programming language person's perspective, if you have a program that branches on some secret variable, right? So the secret variable can be the last bit of your secret key. And then depending on the value of the secret variable, you can either read memory location X or Y. So for any program that has this secret branching behavior, if the memory access patterns in the two branches are different, just by observing the memory access patterns, you can infer the value of the secret variable. And so there are many examples of attacks that have been shown earlier where access patterns leak very sensitive information. So I'm just going to give you one more example. And this is an attack performed by researchers in UT Austin as well as Microsoft Research, and they were running commercial image processing software inside SGX Enclave. And they were only observing coarse-grained access patterns, meaning page-level access patterns. And they showed by using this access pattern, they can recover the shape and location of the objects. So it leaks a lot of sensitive information about the image being processed. Okay, so now the question we want to ask is, can we provably defeat access pattern leakage in a way that preserves the efficiency of the program? Okay, so there are two important things here. One is we want proof for security, and the other is we still want efficiency. Okay, so let's continue with Signal's story, right? So Signal back in 2017, they realized, okay, this access pattern is a big problem, so we are going to try to hide access patterns. And they first implemented the naive solution, which is linearly scan through the whole database to answer any query. But they did it in a more smart way. So they say, okay, let's batch together, a bunch of queries, and we can serve the batch with a single linear scan. But I mean, obviously, the batch maybe makes it slightly better, but nonetheless, the overhead is very high because in Signal's case, their database is has billions of users, and a linear scan is just kind of crazy. And the overhead is linear, so I write n over beta. N is database size, and beta is the batch size. And in order to serve their load using this batch linear scan algorithm, Signal had to spin up 500 servers to serve the entire load. And eventually, they realized, oh, okay, this is perhaps not the smartest idea. There is actually a very simple algorithm called path-ORAM that allows them to do exactly the same, but with only, let's say, log squared overhead. This was actually a paper that we published back in 2013. And I also want to mention, so even though the overhead looks like it's log squared, in practice, it's actually just, you observe really just log overhead because the two logs have different bases. Like one of them has a large base. So that log is just like 2 or 3 in practice. Okay, and then after they implemented path-ORAM and deployed it, and they were able to cut down to 6 servers. So this saved them 100x server cost. Okay, so I hope this triggered your interest in learning about ORAM, right? And this is what we are going to talk about next. So what is this mysterious path-ORAM algorithm? And we can together try to construct an ORAM algorithm step by step. So let me first quickly mention what is ORAM. It's an algorithm technique that probably, I call it encrypts access patterns because the security you get is as strong as encryption. But of course, you can encrypt data, but it's not clear how to encrypt access patterns because access patterns are a side effect of program execution. But behind the scenes, essentially, you're commuting the data blocks in memory and you're shuffling them as you access the data. So you'll see exactly how it works. As an abstraction, right, ORAM takes in the logical addresses you want to read and write, and it will translate these logical addresses into a sequence of physical requests. So we are going to assume the adversary can obviously observe the physical reads and writes. And for an ORAM scheme to be secure, we want to make sure that the physical access patterns are independent of the input requests. So no matter what the input requests are, the sequence of physical reads and writes you make are indistinguishable. So that's the security requirement. And if you were to deploy ORAM together with hardware enclave, right? So here's the security boundary. So essentially ORAM would be running inside the enclave. And we are going to assume the adversary can observe the access patterns outside the enclave. Okay. So I want to tell you, how we started working on ORAM and how things, evolved over time. So I started working on ORAM back in 2011. And back then, this was the landscape. So Goldrick and Ostrovsky, they were the first to propose ORAM. And this was back in the 1980s. And they showed a very non-trivial result. They show, okay, besides this naive linear scan scheme that you can do, linear scan takes n cost, but they showed you can actually get it with only log cubed cost. So from a theoretical perspective, this is very non-trivial, right? From linear to log cubed. But their algorithm is very complex and it has very large constants. The constants are actually astronomical because they use like some expander graphs. So the scheme is not practical in practice. And on the other hand, what's interesting is Goldrick and Ostrowski, they prove a lower bound on the performance of any Oblivious RAM algorithm that can compile a generic program into an Oblivious counterpart. So they show any such generic Oblivious compiler has to suffer from logarithmic overhead. So basically, if your original program runs in time t, you have to run in time t log n operator. Okay. So I was like faced with this landscape when I started working on this problem. And I also want to quickly mention, actually, there were a line of work before ours that tried to improve Goldrick and Ostrowski's construction. They were able to reduce one of the log factors, so from log cubed to log squared. But all of these schemes, they were building directly on top of the algorithmic framework originally proposed by Goldrick and Ostrowski. So these schemes still suffer from the same drawbacks. They're complex and they have large constants, and they're not the best fit for practical implementation. So I realized, okay, here are the important questions for ORAM back in 2011, right? So of course, one big question is, okay, can we take ORAM, which was back then a theoretical concept, can we actually make it practical? And the second obvious question is like, oh, there is actually a gap between the upper bound, which is log cubed or log squared, and the lower bound, which is log n. Can we bridge this gap? Can we either find an asymptotically optimal ORAM scheme, or can we prove a stronger lower bound? And in our research in the next 10 years, we were able to answer both of these questions, right? Like on the practical side, we were able to construct really simple and very efficient ORAM schemes, which now has large-scale deployment in practice. And we were also able to resolve this theoretical mystery. Like we constructed a asymptotically optimal ORAM scheme that's only log n overhead. The practical scheme and the theoretically optimal scheme, they're not the same scheme. Like it would have been nice if they were the same. Today, I'm going to talk about the practical construction. The theoretical one is quite a bit more complicated. Okay, so now let's really think about how to construct an ORAM. And the first idea that will pop up in your mind is, okay, why don't we just take all the memory blocks, permute them in memory? And I'm going to assume the permutation is kept secret from the adversary. So let's say the CPU knows the key, the seed of the permutation, but the adversary doesn't know what random permutation you have applied. And the advantage of this is like right now, if I want to access some logical address, let's say I want to access logical address 9, I'm just going to go to a random location, right? Okay, so it seems like this may give you some security, but it's not exactly secure. And the problem is that it will leak statistical information. Like for instance, if I have 2 consecutive accesses to the same block, the adversary can observe, oh, okay, now you access the same block twice. So it leaks things like frequency, and it also leaks high order statistics like co-occurrence. Like in the specific case of Signal, even if you just randomly permuted the user records, it will still leak the social network graph. And from the social network graph, like if you have some other public social network graph, you can kind of run some practical graph isomorphism algorithm to like align these 2 graphs and de-anonymize the nodes. And this was shown, like I had a paper back in 2011 showing like these practical graphs are very easy to de-anonymize. Okay, so essentially if you only apply the random permutation to the memory blocks, it's not sufficient for security. Like this naive algorithm only gives you security if you access every block only once. Like if you are promised, okay, I'm going to access every block only once, you are fine. But if you repeatedly access the blocks, you end up leaking statistical information like frequency and co-occurrence. And actually, I want to quickly mention, for the same reason, deterministic encryption is also not secure. It's because it leaks statistical information. Okay, so now let's think about how to fix this problem, right? So the lesson we have learned from this naive permutation idea is that it seems like if we want to have an ORAM scheme with a non-trivial performance, the blocks have to move around in memory. And in fact, actually, every time you access a block, you have to relocate it to a new location, because otherwise, if you access it again, you are going to go back to the same location, which leaks frequency. Okay, so I want you to keep this insight in mind when I introduce the algorithm, because we'll see this important insight again. Okay, so our algorithm is based on the tree data structure. Every node in the tree is called a bucket. And a bucket has finite capacity. It can store blocks. And some of these blocks are real blocks, and some of them are filler blocks. So the filler blocks are only there for security. They don't store any real data. I'm also going to assume that all the blocks are already encrypted. And when you read a block, like, you're going to read an encrypted block. And when you write a block, or even if you just want to re-encrypt it, even if you just want to read it, you will always re-encrypt it and write it back. So the adversary cannot see, like, which block you have written. Okay, so the only thing the adversary can observe is the access patterns. Okay, so now, so let me first cheat a little bit and assume the CPU can store a position map. So the position map stores the following important information. So for every block, I'm going to assign it to a path from the root to some leaf. So in this case, let's say block X is start on the blue path. So it's guaranteed that the block X will reside somewhere on the path, which means if I want to read block X, all I have to do is I can look up the position map, find out X is on the blue path, and then I'm going to scan the whole blue path. I'm guaranteed to find X. And so once I read X, I'm going to remove it from this path. And now, like, the CPU is basically holding this block X. Okay, so I want to quickly mention that this assumption that the CPU stores the position map is a very strong assumption, because the position map is very large. But I want you to not have to worry about it, because later on, I will actually get rid of the position map entirely. Okay. Okay, so now it comes back to the key insight I have mentioned, right? So now I have read block X. The most important thing is I have to relocate it immediately, because otherwise, if I read it again, I'll end up looking at the same path, which leaks information. Okay, so how do I relocate the block? The most natural idea is I will pick a new path and just assign it to a new path, and I can pick the new path at random. So suppose I happen to pick the green path, and I want to relocate this block to the green path. So I have to decide where on the green path I can write the block to. Okay, so let's try some ideas. Like, can we write the block X to the leaf on the green path? Unfortunately, the answer is no. Like, can we write it to this leaf node? Unfortunately, the answer is no, because if you write it directly to the leaf, you end up leaking the new path. So let's say next time I access the same block, you'll go back to this green path, right? So you can still observe the linkability. And the key here is, like, I need to write it to the new path without disclosing which path I have chosen, right? So for similar reason, like if you write to any of the internal nodes, it's also not secure, because even though you don't leak the whole path, you leak some partial information about the choice of the path. So what I really want is I want to write to the green path without leaking which path I have chosen. So the only safe place for me to write it to is the root bucket. Because the root bucket is on every path, when you write it to the root bucket, it doesn't leak any information about the choice of the path. Okay, so this is kind of like the basic idea. Of course, the scheme doesn't work yet, like, because for one thing, I cannot keep writing things to the root. The root will soon overflow, like it has finite capacity, right? But setting this problem aside for the time being, like, I want to point out, if you have a scheme that has this kind of structure, the security proof is actually trivial, because the key observation is every time I read something, I write it to a new path, but without disclosing which path it is. So this means every time I want to read a block, I just visit a random path, and the choice of this path has not been disclosed before. Okay, so you can see, like, this doesn't leak any information, because the only thing the adversary sees is every time you're accessing a random path. But to make the scheme actually work, there are a couple problems we still have to resolve. Like one is, like I said, there's this overflow problem, like we cannot keep writing things to the root. And secondly, besides the overflow problem, I promised you earlier that I will get rid of the position map. Okay, so I will quickly comment on how to resolve these problems. So first, how to resolve the overflow problem. And the idea is that we are going to introduce a background eviction process. So this is kind of like the maintenance work I have to do to make sure none of the buckets will ever overflow. So you can imagine in the background, I'm trying to move blocks towards the leaves. And when I do the eviction, I still have to respect the path invariant, that every block is like assigned to some designated path, and blocks can only move along its own designated path. Okay, so this eviction process, I won't go into details, but the access pattern of the eviction process, it can be done in a way such that it doesn't even depend on the request. Like I can use some deterministic eviction schedule, and we can prove that if you evict like this, none of the buckets will overflow with extremely high probability. And in fact, you can make the failure probability as small as the failure probability of encryption. Okay. So this is how to resolve the overflow, and then how to resolve the position map. And this can be summarized with just one word. We are going to use recursion. So in other words, I have this large position map. I mean, it is linear in size, but the size of the position map is smaller than the original database. And this is because within a single block, I can pack the position identifier of a constant number of original blocks. So every time you end up reducing the database size by a constant factor, right? So basically the idea is I'm going to take the position map, store it in a smaller ORAM, and I end up with a smaller position map, and I'm going to recurse on that until at some point the position map becomes just constant in size, and I can store that in the CPU's registers. Okay, so every time if you can reduce the database size by a constant factor, after log n steps of recursion, you end up with the constant size position map. Okay, so this is the idea. I also want to quickly mention, like, remember I said, the scheme has log squared overhead, right? And the two logs, like one of them is coming from the length of the path, and the other one is coming from the recursion. But the log that's coming from the recursion has a very large base, because typically in practice, a block can pack many position identifiers. So that log in practice is just 2 or 3. So in fact, in practice, in the implementation, you just basically observe logarithmic overhead instead of log squared overhead. And the resulting algorithm is actually very simple. It's called pathoram. It's so simple, it only has like 16 lines of pseudocode. And I'm even counting lines like and if and for. It's so simple, you can print it on a t-shirt. Actually, so I also teach this algorithm like in our undergrad algorithms or crypto classes. So this algorithm is actually much easier to teach than, let's say, balanced binary search trees, because this is also like a tree type data structure. It has data structure type of overhead. It's very efficient. Unlike balanced binary search trees, you have to do like rotations. Like here, there's no complicated operations like rotation. So it's actually much easier to understand than, classical data structures. I mean, of course, this data structure is like a privacy data structure, right? It's a different purpose. But I'm just saying in terms of simplicity and efficiency, like a good way to think about it is this is kind of like data structure type of overhead. Okay. So to summarize, I've talked about, ORAM construction. Essentially, we have this binary tree-based data structure, and the key challenge is every time we read a block, we have to relocate it to a new path without disclosing which path it is. Okay. And to summarize my talk, I will end the talk with some kind of thoughts on applications, and including, some of the potential applications in blockchain. Okay, so first, so do you need ORAM? When do you need ORAM? So I drew this simple decision tree, right? When do you need ORAM? Like if you are using trusted hardware, chances are that you need ORAM, because like if you have an interesting computation task that uses like data structures and stuff, that has these dynamic memory access patterns, like you need ORAM for the scheme to be fully secure. Like if you're not using ORAM, you should reflect, oh, actually, is my implementation actually secure? Like it could be you don't realize you need ORAM, but you're just going for insecurity. And also for multi-party computation, oftentimes you also need ORAM. Like this is something I don't have time to talk about, but like suppose I want to do computation on encrypted data using multi-party computation instead of trusted hardware, the same problem will arise. Okay. Blockchain applications. So there are actually many interesting applications in the blockchain context. Like, so for instance, if you want privacy preserving transactions as smart contracts, right, there are many projects that are using trusted hardware for privacy, but today they're not using ORAM. And for this reason, actually today's implementation doesn't actually give the promised security. Like for instance, my student Andrew Miller and his students, they actually did some security analysis of the secret network, and they show, secret network is kind of, they don't achieve the promised security for many reasons. And one of these reasons is like they don't use ORAM. And if you look at the execution traces, like you can see who's the sender of the transaction, who's the recipient of the transaction, which NFT you are trading, things like that. Companies like Flashbots are very interested in Oblivious RAM too. Because like, today, if as you may be aware, like layer 1 is becoming actually more centralized. And there are these big players like Flashbots, and they're kind of selling favorable positions in the block to both, users and to arbitrageurs. And they want to actually provide their customers the assurance that they are not front running and back running their transactions. Because like companies like Flashbots, they're in a very good position to potentially front run, background their customers' transactions. So they want to like shift to SGX implementation of MEV builders. And there you have to do like speculative execution of the EVM smart contracts. And the access patterns there are very leaky. Like it can leak the sender, the recipient, which MEV you are, which NFT you are interested in trading, so on and so forth. Privacy preserving lightweight clients. And there are actually already projects that are using ORAM to provide privacy preserving, retrieval. Like for instance, mobile coin is an example. I won't go into details. So right now, we are working on developing an Oblivious STL library, and you can think of it as like an Oblivious counterpart of the standard C++ STL library. So we are going to provide efficient Oblivious implementations of common data structures like map, set, priority queue, range query data structures, other algorithmic building blocks like sorting, shuffling, common algorithms like graph algorithms, and so on and so forth. So this is ongoing work. Like we just started, but there's obviously a lot of work remaining to do. And partly the reason why we are building this library is because we see many challenges. Yeah, even though these algorithms are very mature, very simple, right? They have data structure like simplicity and overhead. There's still some challenges for practical deployment. So the first challenge is actually like just lack of awareness, which is also a little bit surprising because like ORAM is something that's really simple in comparison with, let's say, something like ZKP, zero knowledge proof. But there's, in general, at least I think for the blockchain community, there's more awareness about zero knowledge proof than ORAM. And if you look at zero knowledge proof, like what's interesting is like zero knowledge proof, there are many different schemes and there's no one size fits all solution because there are many different metrics and some schemes are better at one metric than others, and there's a trade-off. But with ORAM, pretty much for everything you want to do, there's a unified solution. Like we know this is the best scheme, and we know a lower bound for this, and the upper bound is very close to the lower bound. That's pretty much not a lot you can do to improve, the state-of-the-art solution. And also in terms of barrier of entry, because ORAMs are just like simple algorithms and data structures, it should actually be much easier for developers to like develop them and use them in practice than ZKP. There are other challenges, like for instance, you can use a generic ORAM. What generic ORAM gives you is you can take your legacy program, directly compile it to an Oblivious counterpart. But you can also do it more smartly, like you can tailor a specific Oblivious algorithm for your specific computation task. And this can often make your algorithm faster. And this is actually one of the reasons we are building Oblivious STL, because it's like, we want to provide both the generic version where you can just take your legacy program and it's ready to go. But if you want to speed things up, you can also look inside the program and replace like these data structures and non-Oblivious components with, the Oblivious map and set and so on and so forth. And that can be a better approach in terms of efficiency. Oftentimes there's a mismatch of the performance metrics you encounter in practice and the performance metrics that are written in these algorithmic papers. Like one example is if you implement them in SGX. So most of the ORAM papers, they have a single performance metric, which is like, they don't differentiate between the computation cost and the cost of memory reads and writes. Whereas if you implement it in a secure enclave, oftentimes the I/O cost, like the cost to read and write memory pages, will dominate the computation costs. So in practice, like we also want to have implementations in the so-called external memory algorithm model, where we actually optimize for the I/O cost as well. Like besides the computation cost, we also want to optimize for the I/O cost. By I/O, I mean memory reads and writes. Okay. There are other challenges, like for instance, how do you verify your implementation is actually secure? Like for instance, we looked at some existing ORAM implementation, like this is a Oblivious map implementation from a Berkeley group, and we realized it doesn't actually give the promised security because the code has this kind of secret branching behavior, and inside the different branches, the memory traces are different. But this is actually, from an academic perspective, it's a solved problem because we can use these memory trace Oblivious type systems. And what this means is you can throw this code into an Oblivious compiler, and the compiler can automatically tell you, is your code secure or not? And these techniques are very, very mature from like, academic perspective. So I think the next exciting step is just to take it and try to transition it into practical deployment. Okay, so let me end my talk, by quickly mentioning that we have some preliminary open source available, and specifically for this the hardware enclave-based implementations, it's available at the first URL. But of course, like right now, it's kind of like a starting point. We have implemented some primitives, but there's still a long way to go. Okay, so do you need an ORAM? If you come to Pittsburgh, you'll discover like in our coffee shops, they sell these ORAM donuts. So yes, you need an ORAM because they're delicious. If you come to Pittsburgh, I'll buy you an ORAM. Thank you.